Hello Physics 100 students. This is the first video for Chapter 11, which is on electricity. The first thing we're going to talk about is just a little bit of history, and that is the electrification of the United States. So a couple of points, not necessarily in order. We're going to go back to the electric utility and when it started with Edison and Tesla and Westinghouse and all the controversies of the late 1880s and 1890s, which is really kind of interesting. But before we do that, let's talk about a Roper poll. So in 1999, a Roper poll concluded that less than a third of consumers, which is you and I, understand where their electricity comes from, which is absolutely amazing when you think about it. The electricity, you just see a plug in your house and you put all your devices into it, your blow dryer, your blender, your microwave oven, and you don't take the time to think of where that electricity is coming from. Okay, so the second note is, or that the electric generation is responsible for a third of all greenhouse gas emissions. So we tend to over-focus on the transportation sector, but a third of the greenhouse gases are lost from the electricity that we generate, because especially in the United States, most of the electricity is generated by burning fossil fuels. So even though you are not directly creating a greenhouse gas when you plug in your vacuum cleaner, back at the power plant, they burned natural gas for the most part in Bergen County, or coal, and that burning of natural gas or coal caused a lot of greenhouse gases. Okay, so let's do a little quick history. In 1882, the first power plant for supplying electric power went into operation under the direction of Thomas Edison. It was initially in Lower Manhattan. It served 59 customers, so a very small power plant, and those 59 customers total, now granted they may have been apartment buildings, there may have been factories, they had 1,300 electric lamps. So for the most part, most of that electricity was going into making electricity that was used to make lighting. So just to let's take our 1,300 and just divide it by 59, and we'll see the average number of lamps. It had about 22 lamps, right, in each location. All right, jump ahead. 1978, the Public Utility Regulation Act, okay, occurred, and this opened the way to limited competition in generation, transmission, and distribution of electricity. Before that, if you lived in Bergen County, you had no choice. You had to buy your electricity and have it brought to your home from PSE&G, which is the Public Service Electricity and Gas Company. PS is Public Service, Electric and Gas. Okay? If you lived in New York City, you had no choice. You had to have Con Edison do that. Now, we have an interesting case where you can have your electricity supplied by a third party, but you still have to get a PSE&G bill, because PSE&G runs the lines that carry the electricity to your house. So your bill is broken up into two fractions: the amount that you're buying the electricity and the amount to bring it into your house. And we'll take a look at an electric bill later on. Okay, so enough with the history lesson. Let's have a quick look at the physics. Let me just make this a little bit smaller. Oops, too small. The physics of electricity. How's that? It's probably perfect. Okay, so first concept that we want to talk about is electric current. Electric current is given the symbol capital I. And you can think about it as the flow of electrons in a wire or moving through a wire. If I take a wire, right, which is made out of a material that conducts electricity easier, so usually it's metal, something like silver, copper, or aluminum are three metals that are used for wires, where obviously silver wires would be very expensive. So the majority of our wires are made out of copper. Okay, it's a very good conductor of electricity, and chemically it holds up to nature very well. So here's our copper wire. You can think about it as, in this case, either having a coating of plastic around the outside and the electrons move through the copper metal on the inside, or in this case, since we're not going to touch it any place, you can think about it as a bare copper wire for now. Okay, so what do? I purposefully put an electric field on it. I take a battery and I attach it to the negative terminal on the battery, which is called the anode, and the positive terminal on the battery, which is called the cathode. Okay, so I attach those two things, and what happens is that we know that charged particles repel one another. So the free electrons within the wire that are kind of stacked up on this side, because this side is negative, want to move from the negative side to the positive side. So the driving force is the fact that opposites attract. The conducting material is the electrons, the free electrons moving through, and they move from negative to positive. Okay? So how many coulombs, which is a unit of electric charge, move every second tells you how many amps there are. So 1 amp of electricity is 1 coulomb of electric charge divided by 1 second. This doesn't look like an S, okay? It looks kind of like a small delta, but that's an S. Coulombs per second are amps. So formula for electric charge is Q, which is the number of coulombs, the amount of electric charge divided by time. The more coulombs, the faster you can get the coulombs to move through here, the higher the current will be. Okay, so this first thing, so we have I, right? I is the electric current. Well, we need to define one other critical parameter at this point, and that is the electric potential. Going back to this system up here, if I had my battery and I put a negative lead on this side of the wire and a positive lead on the other side, the difference in those two potentials, how much this one is negative with respect to how much this is positive, is called the voltage. And we're going to measure the voltage in a unit called volts. So typical battery would be a 9-volt battery. Those are the little square black ones with the 2 connectors on the top. So if I attach the 9-volt battery across this, it would get very hot. And this side would be -9 with respect to this. So if you consider this 0, this would be -9. If you consider this guy 0, this would be +9 with respect to it. Okay? So that term, voltage, really is the electrical potential. Capital V is going to be our unit to measure electrical potential. The units are going to also be V, so it's volts, voltage in volts. So the unit of electrical potential is volts. Okay, now what is it underneath? Well, it's the amount of energy that you need to move those charged particles divided by what the charge on those particles is. So it's in the units of joules, which is a unit of energy, per coulomb, which is a unit of electric charge. So charge per coulomb, or joules per coulomb. So let's look at the definition and try to explain it. So the voltage is defined as the work, which is joules, right, energy, the work per unit charge to move an electric charge from point A to point B. Okay, so here's my point A, here's my point B. You can think about it as a wire if you'd like, or you can think about it as an open space. Okay, so if this charged particle, if this charge, this electric charge turns out to be exactly 1 coulomb of charge, okay? Now, let's say on this side, this particular charged particle is positively charged, okay? So it's positively charged because it wants to move towards the negative side. So this side over on A, this side on the left is positive, this side is negative. Okay, so A naturally wants to move across it if it's positive. If that, so what would you have to do is you would have to apply a voltage to keep it there that's equal and opposite to it to hold it back, and that would be the voltage to retard that moving of a charge. But if you think of it as electrons and it's negative, if you take 1 coulomb of electric charge that comes from electrons, I would have to push it against this negative because like particles repel each other. So my 1 coulomb of negativeness, how much work would it take to push this against an electric field of 1 volt? If it was a 1 coulomb charge, it would take 1 joule of energy, right? 1 joule of energy to move this charged particle of 1 coulomb against a field of 1 volt. So a volt is the amount of potential that's required to move 1 joule's worth of electric energy for a charged object. That's 1 coulomb. That's the definition of a volt. So it takes 1 joule of energy to move the charge across here. Okay, if this field was not 1 volt, but 100 volts, it would take 100 joules to move that 1 coulomb charge. If this charged particle was not 1 coulomb, it was 2 coulombs, then it would also take twice as much because it's the joules for each coulomb. Okay? So anytime the amount of charge goes up or the voltage goes up, it's going to take more work to fight against nature, where nature wants to have negative things attracted to positive things or negative things repelled from other negative things. Okay? So volts are joules per coulomb. Okay, so let me just finish up this note at the bottom here. I'll put these 2 sections together so you can read the whole thing. It takes 1 joule of electric energy to move a charge of 1 coulomb through an electric potential of 1 volt. This would be a great thing to have around when you took the test. That's the definition of a volt. The amount of work it takes to move a charge of 1 coulomb through a potential of 1 volt. Okay, so we have 2 critical units so far that describe our electrical system, and that is capital V is the voltage and capital I is the electric current. Okay, let's talk about different kinds of electric current. Oh, we're going to have a third one in a little bit. That's going to be capital R, and that's going to be the resistance. So those 3 things we're going to put together in an important formula. They're all capitals. The resistance is how hard it is to push those electrons through that particular wire. An electrical conductor that, like this wire here, that's very easy for electrons to move through, would have a low resistance. The wire, you would not lose a lot of energy to heat by moving it through here. If you change the material to something that didn't conduct electricity very well, and you'd have to fight and force your way through there, it would have a higher resistance. So the resistance is going to be the loss of energy from moving the charged particles through the wire or through the device, whether it be a motor or something like a heater or an electric light bulb. The resistance is the amount, how hard it is to push those electrons through because they don't want to go so easily. The higher the resistance, the harder it's going to be. Okay. Here's a couple of types of electric current. So the first kind is the kind that you think of, it's called DC or direct current. So let me give you some applications where you find direct current circuits. Okay. Inside your computer battery charges up your computer in DC. So your computer basically runs on DC. So does your iPhone. So does most of the electronic objects that we have inside our house. They are DC. They come into the device and then they get changed through from AC to DC because our electric systems in the walls are all alternating current. Okay, electronic equipment is DC. Another thing that's DC would be a simple flashlight. Okay, batteries are direct current. One side of the battery is positive, the other side of the battery is negative. So here's an example of what would happen if you were looking at the voltage across a DC circuit. Okay, so I'll show you what the circuit looks like, and then what we're going to do here is we're going to track the voltage versus time as soon as I turn on the device. So this little t here is time. This voltage would be, we're starting at 0, so before the experiment starts, I have no voltage. If I go positive, this is going to go up. If I go negative with respect to that original 0, okay, so the thing that I'm monitoring turns out to be negatively charged, I would drop down, okay? So this wire, on purpose, we're going to make, anytime we attach leads, we're going to attach the red wire to the positive lead and the black wire to the negative lead, okay? Now, in this particular case, we're also going to have this little cool symbol over here that anytime I draw it, it means that the circuit is grounded. So if I do something like that, here comes the wire and it goes into this, this means that it's a ground. So it's attached to the same electric potential as the earth is. So I take something and I stab it into the ground so that relative to the earth, that's going to be the 0. So I do that on purpose. Okay? So a lot of times our systems are grounded. One of the two leads, either the positive or the negative. And in all of the circuits that we use in everyday life, it's the negative, it's the black lead that tends to be grounded. That's equal to the voltage of whatever the world is or the area around it. And then the positive is going to be positive relative to that. So instead of having both of them floating where they can both be adjusting, we tend to ground one of them, and it's usually the negative one. It didn't have to be, but we tend to all do it the same way. Okay, so here's what the device looks like. I have a very, very simple circuit. You can think about this as a 9-volt battery, so one of those small little box batteries, right? These guys are a little bit different. One of them has something like this on it, and the other one just is a knob, right? So they're a little bit different, so you can't attach them the wrong way. So in this particular circuit, what do? First thing is I attach a wire to the negative, and I attach it to a light bulb, okay? Now, light bulbs really have a little knob on the bottom, and that little knob on the bottom is going to turn out to be different than the screw-in part on the sides. So instead of my wire coming over here, I actually should have attached it to that little tip at the bottom here. Okay, but let's say it's in some kind of housing where this wire comes in and attaches to the bottom of the light bulb, and this wire comes in and attaches to the screw part of the light bulb. Okay, so this is the load. This is the resistor. This is the thing that's going to use up the energy, that's going to take that electric energy and turn it into heat and light. Now, in an old-fashioned incandescent light bulb like Thomas Edison had, it was mostly heat that's wasted and a small amount of light, and we just lived with that loss of heat to get the light out. Now, in our lifetime, we've replaced incandescent light bulbs with first compact fluorescent bulbs, which are probably 6 or 7 times more efficient. They run on a similar process, but the percentage of light energy compared to heat is much higher. And then, in the last 10 years, we've even replaced the compact fluorescent bulbs with what we're buying now, which are LEDs. So you put an LED in there, and they're even more efficient and long-lasting, which means that the electric energy is converted at a higher percentage into light. Less heat is lost as heat. Okay, so, but in any case, I attach it to the circuit. One side is negative, the other side is positive, and this guy comes down into here. You can also run incandescent light bulbs on AC circuits. You can run complex fluorescent on AC, and you can run LEDs on fluorescent. And the reason is because inside the base there's a transformer or a circuitry that changes it from AC to DC. So that's built into the body. And that's what makes them a little bit more expensive, is you have to do that conversion from AC to DC right in the base. But in our case, we just have electrons flowing in one direction. So the moment so here comes the electrons, create the light, they lose a little bit of energy, they come back down to this side. Why? Because they're attracted to the positive. Electrons are E-, they have a negative charge. They're repelled from the positive, and attracted, from the negative and attracted to the positive. So as soon as I attach this wire and this light bulb, they would rather go through here than hang out over here, because there's a lot of negativeness over here, and they're negative, and negative hates negative. So they're attracted. That's the driving force. They're pulled through and come down into here. They get recharged and sent back out again. Okay, the last thing that we do is we take this wire. It seems crazy, but we just attach it to something and we hit it to a piece of metal inside our house, or if we were outside, we could just attach it to, we could just put a stake into the ground and attach a wire. Now, with a flashlight that runs this way, the whole outside of the container, right, is actually negatively charged. So when you're touching your hand, you're kind of the ground. So the negative is set at 0, and if this was a 9-volt battery, this positive would be 9 volts higher than 0. Okay, so what's keeping it at 0? What's keeping it at 0 is this wire. It's keeping this side at 0. So this one is going to be positive with respect to it. Okay, so here we go. Here goes the experiment. The moment let's say this circuit was broken and I didn't attach the wire, right? The moment I attach the wire right here, so I had a little switch here, and right now it's off when I have my finger over it. As soon as I take my finger off of it, I turn it on. Well, what's going to happen is there actually is going to be a tiny lead time. It's going to take a split second. You're not going to notice it, but in a millivolt, boom, I turn it on. It's going to go up. It's going to reach its maximum potential of 9 volts, and it's just going to stay there. Super boring. It's going to be at a voltage of 9 volts as long as the flashlight is running. Eventually, as the flashlight starts to die down and you see its light not so bright, it might drop down to 8 point something, but it's never going to get to 0. The light will go off because there isn't enough voltage to push it through before the battery runs down to 0. Your battery usually has some energy left, but it's not really useful for any application. Okay, do the same thing, not with a DC power supply, but do it like you would in your home with an alternating circuit. So this is alternating current. AC means alternating current. It's an example of an AC circuit with a ground. Okay, so the moment I turn the device on, what I start to see is that it goes positive and negative on a continual sinusoidal path. It looks like a sine wave or a cosine wave like you learn in math class, okay? Mine looks like it's tailing off, but it shouldn't. It should go up to a height and then down to another height. And I'll tell you what those two numbers are in a second. Okay, so let me show you what the circuit, okay? Instead of having a positive and a negative, my AC power supply, sometimes you'll see it written like this, just a circle with this cool little symbol inside, okay? My AC power supply is going to provide this positive and negative, up and down, voltage, okay? And I don't have one of them that's red or one of them that's black, which is always positive and always negative. What it is one of them is called the hot wire. And the hot wire is the wire that's attached directly to the power supply. It's the one where the energy is being generated from, and this sine wave of positive to negativeness is created. In your house, that's usually the white wire. That's usually, sometimes it's brown, or it's black, or it's red, okay? So that's going to be the hot one. The neutral is usually white. So coming off the other side of the light bulb, here comes the electric energy going positive, negative, positive, negative, positive, negative, positive, negative, positive, negative, positive, negative. Shooting through here, if you don't attach the other side, there's no place to complete the circuit, right? So it wouldn't go on. Even if I didn't have that, I need to ground it. So I could ground it to the earth, but more than anything, we ground it back to the positive, and that's called a neutral. So many times your systems will have a third wire, which is green, called a ground. There's not really that much difference between the neutral and the ground. The ground would just be attached to keep the neutral equal to the ground. But the ground kind of, sorry, my screen went off. The ground we can think of, the neutral we can think of as going back to the power supply, back to PSE&G, and the ground, which runs parallel to it, is just into the ground in the back of your house someplace, on the side of your house. So your house, all of the neutral wires are grounded, okay? But these ones here, or should be, a better way to say it, the neutral wires should be at the same voltage as the ground. So if you touched the end of a neutral wire, one of the white wires, and you touch the green with a voltmeter, you shouldn't see any difference if your house is wired correctly. You should only see the difference in voltage between the hot wire and the neutral, and it actually should be the same value as between the hot wire and the ground. Those neutrals should be grounded. So there's only one dangerous wire in the wiring in your house, even though you have 3 wires running everywhere, right? You've got a white one, either a brown one or a black one. So let's say most people, it's a black one. You have a white one, a black one, and then you have a green one. So what I'm saying is the potential difference, the voltage difference between the white wire in your house and the green wire should be equal to 0. And the hot wire would be at an AC voltage, either positive or negative at any given time relative to those two. Okay, so works the same way. Okay, I couldn't tell the difference between the light if it was AC or DC. Okay, so what does it look like? Turn it on. Instead of just going up and sitting at positive, it's going to go up and down, up and down, up and down. So for our homes, the electricity that comes through our homes, all of our appliances run on AC. So not our computers or our televisions or our smartphones, but things like blenders, any motors, fans, air conditioning. So what do they run on? Well, they run at the frequency and the voltage that's coming out of the plug. So down in your basement, you have 220 volt electricity coming from PSE&G, and then you have a transformer that cuts it down to 110, and 110 is distributed throughout your house to all of the outlets. Okay? If you have a special appliance, like something that's going to use a lot of electricity, it may have a 210 volt line dedicated to come in for a refrigerator or some other device that you have, or for instance, your air conditioning is probably runs at 220. Everything else, all of the regular outlets are going to be at 110. Okay, so what's happening? What's happening is that PSE&G is sending out the electricity at 60 cycles per second. So that means every second, this thing is going to go positive and negative 60 times. So the frequency is 60 hertz. That's the regular AC power that we get. So AC that comes into our house is 60 hertz. 60 cycles up and down per second. That's what hertz means. Okay? How many times does the cycle go up and down? So that's the first thing. What's that called? That's the frequency. Okay? What's the voltage? Well, the voltage peak to peak is from the top of this crest to the bottom of the next one. If I look at what's that net difference in electricity, the stuff that's coming out of your outlets is between 110 and 120 volts. We usually call it 110. If you plugged in, you might see in your house it might be 114, it might be 115. We just call it 110, but it's usually not more than 120. Okay, so that's the voltage. The current, how many electrons, how many coulombs of energy per second are coming into your house depend on the device. If you're pulling a lot of electricity because you're using a drill or a blow dryer, you're going to have a much higher current than you would if you don't. What's not going to change is the frequency and the voltage. Those two things are not going to depend on which appliance you use. All of the appliances are going to run on 110 volts and have a frequency of 60 hertz. So that's AC. Done with that example. That's page 4 of the notes. And again, this little symbol over here is usually the way you depict an AC circuit. Okay. Okay, a little review on what batteries do. Batteries, by definition, okay, but by the way that they use, they are always going to be DC. And how do they work? They convert chemical potential energy, which are reactants inside the battery that want to occur, or reactions inside the battery that want to occur, into electrical potential energy. When we recharge the battery, we drive those chemical reactions backwards. So they're going to give us, the chemical reactions are going to occur to give us free electrons that travel through the circuit that we can use for DC electricity. When we charge them up, we put the electric energy in, and those electrons flow backwards to create chemicals that can later on be used. So we're basically pushing the reactions backward when we recharge our cell phone. So think about the battery inside of your cell phone. When it's dead and you're charging it up, you're making chemical reactions occur inside the cell phone battery that you can use later on when you need it, when you are using your cell phone and it's not plugged in. They're going to run. They would run forward. Okay. So I'm going to show you these two figures right now. It says review figures 10.5 on page 315, which is a lead storage battery. So let me do that right now. So this is from the old book. So here's page 315. I'll show it to you quickly. Okay. So in a lead storage battery, and one example of a lead storage battery is the battery that is inside of inside your car. So so this would be like a typical example would be a car battery. Okay. So what you have is you put two electrodes into a solution, and that solution has a very strong acid, sulfuric acid. So these chemical reactions, they really don't have that much to do with the sulfuric acid, but they just need to occur in a very acidic environment. So that's why we do them in sulfuric acid. This one is a lead electrode. This one is a lead oxide electrode. Okay? They are not touching on purpose. Okay? So what happens is when you attach an electric wire, you attach a wire to it, and then you put a resistor. So here's a new symbol that we have. Whenever you draw a squiggly line, that's going to be like your light bulb or your starter on your engine. The squiggly line is going to be the load. It's going to be your blow dryer. It's going to be whatever is taking up the electricity. This is the load. So we're not going to always draw what it is. Okay, we're just going to have this squiggly line, which means that I have a resistance. Okay, so picture it, in this case, make it an electric light bulb or the starter on your engine for your car. Okay, or the radio, right? You want to run the radio. So that's what that is. This is the load. This is where the electricity is going. Okay, so I push it out. So what happens is that the lead down here goes into solution, becomes lead plus 2, and frees up 2 electrons. This is called an oxidation reduction. Those 2 electrons can't travel through the solution, so they build up on this metal. And as this metal becomes negatively charged, they're like, hey, I want out of here. I'm an electron, and I'm on a negatively charged object. So what are they going to do? They're going to flow through the piece of lead, which is conductive, through the wire, push through the load to create the work or do whatever it is that I need to do. Listen to the radio, have my headlights on in the car if the engine isn't running, whatever it is, or have the fan on, or the air conditioner is not going to run, but anything else that you have in your car, right? If you have a lamp on or something like that. Okay, then they have to come out the other side with less energy, but they still come out the other side. They come out the other side and they build up on here on the lead plus 2, on the lead oxide electrode. On the lead oxide electrode, it reacts with sulfate ions that are moving across the solution that are negatively charged, plus 4 hydrogen ions, and the 2 electrons that come through the wire. All of those things happen on this side. This is called the reduction side because electrons are going in to make lead sulfate and water. So the lead sulfate then would just build up on here and fall off into the solution. So what's happening is electrons are created here and used up here. So this is what would happen, the direction that it would occur when you were using your battery. When you're driving down the road and the alternator is charging your battery, you create enough potential energy. Let's say this thing ordinarily gives up 9 volts of electricity. Okay, so it's a 9 volt battery. I think they're either 9 or 12 that are in a car. I should check. Actually, let's make up 12. So when you're using the battery, when the car is not running, you're going to have 12 volts across this way, and the 12 volt is going to be freely coming from the battery. Okay. When you're driving down the road, you're recharging the battery, your alternator is creating energy, it's being converted to DC before it hits the battery, and then it's being pushed into the battery. And guess what? If you put 12 volts in the wrong direction against this, you can push those electrons and force these chemical reactions back the wrong way to build up the lead again, remove the lead sulfate, and you have that energy for later on. So this goes forward when you're using the battery, when you're recharging the battery because your alternator is recharging the battery, driving down the road or even idling, you're recharging the battery all the time. That's why you shouldn't have to change your battery unless it really gets old and every couple of years. Okay? You're constantly, the function of the alternator is to recharge your battery. So this description is very much a car battery. Okay? Let's take a quick look at a dry cell here. So this is a dry cell, which we could think of as a D or a C battery, or one of those. They're about 1.5 voltage different. The little nibby part up at the top, okay, is positive. It's usually positive 1.5 next to the base. The base is grounded. That's going to be the negative side. So these guys are always the little piece that comes up. The one that's harder to get to is going to be the positive. So what do you have inside here? You have an outer zinc can. That's the negative terminal. Inside, you have an electrolyte, which is a moist ammonium chloride solid that's in here. So this allows the flow of ions to complete the circuit, because you can't really have a liquid in it, right? Because it would be too dangerous. Okay, you wouldn't want to have the liquid could pour out if the battery's broke. So a car battery has a liquid inside of it because it's even though it's in a car, it's not, so nobody has it in their hand at any one time. But these kind of dry cells, the sulfates that move across here to complete the circuit kind of move through this moist ammonium chloride buffer in between. And what's in the middle? The middle is a carbon rod. So the chemical reactions occur between the carbon rod and the zinc outside, okay? And so electrons are going to be moving in the same way from the negative to the positive. So the zinc is going to go on the inside of the can, is going to turn into zinc plus 2, give up 2 electrons. Those 2 electrons are going to flow back through the carbon, and they're going to be collected by the carbon. And the counter ion that's going to move across it is the chloride ion. So as electrons move this way, chloride ions have to move that way, because you always have to complete the circuit so that the electricity can go around. Both of these are examples of DC electricity. Okay. So I'll talk about the next note here. I'm going to finish this on today's lesson on Chapter 5, but let's talk a little bit about electric-powered vehicles. The interesting thing is, when automobiles were first coming onto the market in the early 1900s, there was an equal number of electric vehicles as there were internal combustion engines. Okay, so we could have went either way. Way back in 1914, there were 20,000 electric vehicles on the road. So picture a Model T looking car that runs on a battery and an electric motor, right? A DC electric motor, and you would charge it up. So why didn't that take off, 100 years ago? Well, what happened is that once we found that there was so much petroleum in the earth in the 1890s and early 1900s, petroleum was easily made into a logistical fuel called gasoline. You could get gallons of gasoline, you could bring them to gas stations all across the country, put them in tanks that were underground, pump the gas out, and put them into cars. So it was much easier to refill the cars with gasoline than it was to recharge the batteries. So a lot of politics that went into this. Again, in countries around the world, we could have went either way, but in all cases, we went to cars that use internal combustion engines. They could go faster, we could fill them up quicker, and most importantly, a network of gas stations was built out across the country by companies called like Standard Oil. And originally they were accused of having monopolies on that you had to buy your gas from Standard Oil or you had no choice. And the people who were who own Standard Oil are the Rockefellers, which are a famous family in New York that made Rockefeller Center. So maybe they made Rockefeller Center out of the guilt that they made because they had a monopoly on selling gasoline throughout the country. And then once that was broken up, that laws were put in place that you couldn't own every gas station on every corner, so that people had a choice between different companies. So other companies came onto the market. There's a few of them left. There were probably 50 gasoline kinds of companies. Now you guys see out there's probably really ExxonMobil. It's probably just a few American companies and then a few foreign companies. We probably around here have a choice of probably 5 or 6 different gas stations, right? We have BP, Valero, ExxonMobil. I don't think Sunoco exists anymore, right? Getty, you'll see a little bit. And Lukoil, right? Those are the ones that we see around here. So tell me if I missed any, but there's not a lot of choices for the big gasoline companies, right? But at least there's laws that prevent one company from having every single gas station along the road, because then they could control the price of the gasoline. There would be no competition, okay? So some people, maybe you guys do, shop around for their gas. I usually don't do that, okay? I just trust that market value will keep them all about the same. But once in a while, there are people who do shop around. Other neat thing is that the taxes for gasoline in New Jersey are cheaper than they are for New York. So if you ever look on route, anytime you go from New York into New Jersey, especially if there's no toll involved, like going into when you go up towards Suffern on Route 17, you'll see a lot of people get off the last exit on Route 17. You'll see a lot of gas stations there because gasoline is cheaper in New Jersey than it is in New York. Why? Because the taxes are lower in New Jersey than they are in New York on gasoline. We have some refineries here, so we're a little bit more friendly to the gasoline companies than they are in New York. Okay, so batteries have always been the weak link in the development of electric vehicles. The motors are fantastic. Regenerative braking is fantastic. There's no issue with any of that. It's just the batteries. If we could make cheap, efficient, light batteries, we could have went with electric cars a long, long time ago. Again, 3 big things, right? We need to make them lighter so that when we put them into the car, we don't waste a huge amount of the electricity just pushing the batteries around. Think about that, right? So the lighter you can make the batteries, the better. The cheaper you can make them, the better. Right? And the easier they are to charge up, the faster you can recharge them. So those are the big 3. Okay? So some people call it the charge density per mass, right? So for each kilogram of battery, how much charge density can you put in? You want that number to be as high as possible. This way you need less batteries in the car. Okay? Good. All right, a couple of other things I'm going to show you before we wrap up. This is kind of cool from the old book. This is page 316. Make it a little bigger. This shows you the way that the batteries are set up in a typical electric car today. So the first thing we need to do is we need to connect. So I make these 2 connections when I plug my car. In, I have a charger, right? So this charger, right? This can be, usually it's outside the car, and we have 110 going in. So this would be if my car charged at 110. Now, Tesla's charge in your house at 220. Any electric car company you're going to charge at 220 in your house. Only in a rare moment would you want to attach to AC at 110. The reason is it takes so long. It would take you probably 3 days to charge your car fully if you only were able to use 110. But in an emergency, all of the cars have an adapter that they could plug into a regular wall, just in case you're at grandma's house and she doesn't have an electric car charger, which she probably doesn't. Okay, but in your house, you buy the electric car, you put something in your house that uses the 220 in your house, and you charge the car up at that higher voltage. Okay, so it goes from AC inside the charger to DC. So you have a positive lead and a negative lead because, again, all batteries are DC, right? So when you're charging the car up, this controller is off. You're not running the motor, so you can forget about everything over here. All that you're doing is pushing that positive charge, which is the oddball one, right? Remember, everything else is grounded, through here and charging this battery, and then it's going to charge this battery, and then it's going to charge this battery. These three batteries are in series, which means they're one after the other. Look at the way the electricity has to flow. It has to go through the first battery to get to the second battery. So in this particular case, these three batteries are shown in series. If they were in parallel, then I would draw them slightly different, that they would be across from one another, and the electricity could have a choice and go one way or go another way or go a third way. In your electric car, you have batteries that are both in series and in parallel. Okay, so there's a big array, and there might be 15 batteries that are in series with one another, and then 10 sets of those arrays. Okay, so I'd have 15 times 10, 150 batteries in my car, which would really be 10 sets of 15 series sets. Okay, so they put them in both ways, and we'll talk about later on why you would do that. Okay, so once these things all get charged, I disconnect the charger, and now I want to drive down the road, put my foot on the gas. What does the controller do? The controller opens up this circuit. When you press the you press the accelerator with your foot, it electronically controls this circuit and lets more of those electrons, and I can think about them going through this way, okay? So it gets more of them that comes up into here. So you can make a motor that is DC or AC. In this case, we can have the motor being DC. They don't show one side being positive and one side being negative. So we'll look at that. But there are AC motors and DC motors. So it depends on the company, okay? So let's read this down here and see if there's anything else that I want to add to it. So it says basic circuits for electric vehicles. The charger feeds the battery, which can then supply power to the motor to move the car. The speed and power of the motor are regulated by the controller, which in turn is controlled by the accelerator. Okay, so in this case, let's keep it simple. Let's assume that this is a DC motor, so one of these is negative and one of these is positive. Okay. Okay, and again, we'll talk about how the motor works later on. We have talked about that a little bit. Just want to show you two more things really quickly. These are kind of a couple of nice diagrams at the bottom of 306 in the old book. Okay, so I'll put the key down here too. Let me get a little bit. Okay, so let's take a look at this top diagram. So this is from 1949 to 2010. So A says U.S. production of electric by type of generation. Okay, so in the United States, originally, most of our electricity came from coal. Okay, this is trillions of kilowatt hours. So you see, the other lines down here, way back in 1950, were minuscule. You couldn't even see them. So As a country, we used a lot less electricity than we use now. 2000, we kind of peaked, and then we've been kind of going straight across. This guy stops at 2010. But you see, most of the electricity in the United States up through 2010 was still from coal-fired power plants. Again, none that I know of in Bergen County, but in Passaic County, right in Jersey City, there's a huge coal-fired power plant. And you can see it right when, if you take the Bergen County line, as soon as you're coming into Hoboken, you go past this giant brick building that from the 1900s, and that's a coal-fired power plant. And you just see the coal yard just shoving coal. Like there's this big elevator that pulls the coal from the ground, and you can almost see it from the train. Okay, can't see it from the road so much, but you can see it from the train. Okay, so what started to happen is this is petroleum and natural gas, mostly natural gas. Petroleum, guys, is way too valuable. Gasoline is and diesel are way too valuable to burn to make electricity, right? We almost exclusively use the gasoline and the diesel that we create for transportation. So this is mostly natural gas. So here we go through natural gas. Then here, this is nicely, we had a renaissance of natural gas at 2005, and then it dropped back off again, okay? This is partly due to the fracking revolution, and natural gas is a very efficient hydrocarbon, okay? So even though we don't want to burn things, if you're going to pick one to burn, let's burn natural gas. Here's nuclear, okay, which you can see going up and then leveling off. There has not been a new nuclear power plant in the United States since the 1980s, but the amount of electricity they generate, those plants that have already been online, has gone up until 2005 and then leveled off, probably because they made those plants more efficient, okay? So that's how we generate our electricity in the United States. Number one, coal. Number two, nuclear. Number three, this one down here is going to be, this is nuclear here, right? This guy here is natural gas. And then here's hydroelectric. Now the problem with hydroelectric is, listen, there's almost only a limited amount of water that's stuck in lakes that are at high altitude. So if we create, so we can either take advantage of a natural system, and a great example of that is Niagara Falls or the Passaic Falls, right, in Patterson, where there is a natural waterfall, and instead of letting all of the water go over the natural waterfall, we divert some of it and we put it through our system. And when we put it through our system, the water going downhill pushes the turbine to create electricity. Same thing happens with Niagara Falls. With an unnatural system, what we do is there's not a natural waterfall. We create a difference in height and have water uphill by damming off a river. So many examples of that. The most important one is right outside of Las Vegas. It's the Hoover Dam. So the Hoover Dam dams off the Colorado River and makes Lake Mead behind it. And there's a huge difference between the water at the top and the water that's coming out of the bottom. Hundreds of feet of water is held back. So instead of that water just naturally flowing down the river, we force it through a system of giant pipes that are probably 8 feet wide. They turn turbines. The pressure from the water turns the turbines as it goes downhill, and we create electricity. Okay, but again, that can't change very much over time, because where do you get the water from? Where do you get water uphill? Okay, and remember, this is a renewable source here, right? The hydroelectric power, because the sun originally generated the electricity for the hydroelectric, because the sun creates hot spots on the earth, water evaporates, goes up into the atmosphere, creates clouds. Those clouds blow over mountains, and it rains in the mountains. So anytime it rains in the mountains and that water then has a chance to run downhill, you have the opportunity to generate hydroelectric power. So that's what you want. You want rain in the mountains, and then the water runs downhill and you can create electricity out of it. Okay, second graph, and then we'll stop right there. This guy is from 1940 to 2010. And let me read it for you first. It says U.S. electricity production versus GDP from 1950 to 2008. Electricity intensity equals the intensity of these two. Okay, so the GDP is the gross domestic product. So it's how productive in financial terms each American has been. So the gross domestic product has gone up, okay, and leveled off here at 3, okay? So these are relative units on here. So that's what's been happening to the gross domestic product. How much electricity we've been using over time, look at this. They've gone up together, right? The more productive people, more people work in factories. So they've gone up together until about 1995, and then the amount of electricity that we used leveled off, whereas GDP kept growing. Now, one of the reasons is that if we take all of the factory work and we ship it overseas, and we have more people in the service sector, those are not energy intensive jobs, right? So it's manufacturing that's going away, that's partially causing this electricity line to go down. So if you take the ratio of the electricity, right, to the GDP, take this one divided by this one, you kind of get a flat line over time. It's just going down slowly over here. So something else good is happening here. One is as we ship the jobs overseas and we're not doing that factory work here, we're not going to have so much electricity go into industry. So that's one reason for this electricity line to stay low. The other thing is more importantly, and probably the truth is, we have much more efficient light bulbs than we did. They're almost 10 times more efficient than when I was a kid. Okay, so in the last 30 to 40 years, right? The last 40 years from 1980 when everybody had incandescent light bulbs to 2020 when no one does, that's a huge difference in how much electricity is needed to generate it to keep the lights on. Second thing, our air conditioning is much more efficient than it used to be. And our electric generation is much more efficient. Our televisions are much more efficient than when we had a cathode ray tube. All of these things are good, and that's why we have an electric intensity that's dropping and an electric production that's dropping, even as our GDP has gone up. Okay, sorry that these stop at 2010. Okay, so that's everything that I have for you for the first half, and hopefully we'll be able to finish the electricity chapter with just one more video. Okay, thanks guys.